Case study, implementing deep learning models for enhanced cybersecurity, a case study of Cybersecure Inc. Deep learning has become an indispensable asset in countering sophisticated cyber threats. Dr. Emily Chen, the chief data scientist at Cybersecure Inc., was tasked with enhancing the company's cybersecurity posture using advanced AI techniques. Her team, composed of data scientists, cybersecurity experts, and software engineers, embarked on an ambitious project to implement deep learning models for intrusion detection, malware classification, and anomaly detection. The team first focused on intrusion detection systems. They collected vast amounts of network traffic data, comprising both benign and malicious activities. Dr. Chen suggested using recurrent neural networks and long short-term memory networks due to their proficiency in handling sequential data. The choice of LSTM was particularly strategic in avoiding the vanishing gradient problem, which often hampers the training of deep networks. The team wondered, how essential is it to select the right type of neural network for specific data characteristics? After rigorous data preprocessing, they employed LSTM networks to analyze the flow of network packets. This enabled the IDS to detect subtle patterns and anomalies that might indicate an intrusion attempt. However, during the initial testing phase, the model showed signs of overfitting, performing exceptionally well on training data, but poorly on unseen data. Dr. Chen proposed using dropout and regularization techniques to mitigate this issue. Dropout, which involves randomly dropping neurons during training, was particularly effective in reducing the model's dependency on specific neurons. This led to enhanced generalization capability, significantly improving the system's performance on new data. The next challenge was malware classification. Cybersecure Inc. had a repository of binary files, some of which were known malware. Inspired by the success of convolutional neural networks in image recognition tasks, Dr. Chen's team decided to treat binary files as grayscale images and use CNNs to classify them. This innovative approach leveraged CNN's strength in identifying spatial hierarchies to detect patterns within binary files that differentiate benign from malicious software. During the implementation, the team encountered difficulties in determining the optimal architecture and activation functions for their CNN. They experimented with various activation functions, including sigmoid, tanch, and ReLU. ReLU was ultimately chosen for its efficiency and ability to mitigate the vanishing gradient problem, a common issue in deep networks. The team then asked, how do different activation functions impact the learning capabilities of deep learning models in cybersecurity applications? The CNN-based malware classifier achieved remarkably high accuracy, outperforming traditional machine learning methods. However, the team remained vigilant about the potential for overfitting. They employed data augmentation techniques to artificially expand their dataset, improving the model's robustness. This led to a more resilient classifier, capable of handling a broader spectrum of malware. Anomaly detection was the final component of their deep learning-based cybersecurity framework. Autoencoders, a type of unsupervised neural network, were selected for this task. Autoencoders learn compressed representations of input data and try to reconstruct it. Significant reconstruction errors typically signal anomalies. The team collected logs from various systems and network devices and trained the autoencoder on normal behavior patterns. As they analyzed the reconstruction errors, the team noticed a challenge in distinguishing between benign anomalies and potential security threats. This raised a critical question. What strategies can be employed to improve the interpretability of deep learning models in cybersecurity? They explored feature importance analysis and visualization techniques to understand the reasoning behind the model's decisions better. For example, they used heat maps to visualize which parts of the input data contributed most to the reconstruction errors, providing insights into the nature of detected anomalies. Despite the success, Dr. Chen's team faced another significant hurdle: adversarial attacks. These attacks involve subtly altering input data to cause the model to make incorrect predictions. The team conducted adversarial testing on their models, discovering vulnerabilities in both the IDS and malware classifier. To counteract this, they incorporated adversarial training, exposing the models to adversarial examples during training to enhance their robustness. During a brainstorming session, the team discussed the broader implications of transfer learning. Given the scarcity of labeled cybersecurity data, they explored the possibility of repurposing models trained on general network traffic for specific tasks like detecting particular cyber threats. Transfer learning could substantially reduce the data and computational resources required for training new models. This led to an intriguing question: how can transfer learning be effectively applied in cybersecurity to leverage existing models for new threat detection tasks? Dr. Chen's team implemented a transfer learning approach, fine-tuning a pre-trained model on a smaller labeled dataset specific to their security needs. This significantly reduced training time and improved model performance in detecting specialized threats. The success of this approach highlighted the versatility of transfer learning in adapting to different cybersecurity contexts. In conclusion, the case of Cybersecure Inc. provides several insights into applying deep learning theories to enhance cybersecurity measures. The careful selection of neural network types and activation functions is crucial for handling specific data characteristics, as seen with the successful use of LSTM networks for intrusion detection and CNNs for malware classification. Overfitting and underfitting remain persistent challenges, but techniques like dropout, regularization, and data augmentation can mitigate these issues, leading to more robust models. Improving the interpretability of deep learning models is essential for gaining trust and accountability in cybersecurity applications. Visualization techniques and feature importance analysis provide valuable tools for understanding model decisions. Additionally, addressing adversarial attacks through adversarial training enhances the security and reliability of deep learning models. Transfer learning emerges as a powerful strategy in contexts where labeled data is scarce. By fine-tuning pre-trained models, cybersecurity professionals can develop effective and efficient deep learning solutions tailored to specific threat detection tasks. These lessons underscore the importance of a comprehensive approach to applying deep learning theories in cybersecurity, balancing technical excellence with practical considerations to safeguard against evolving cyber threats.